Hello everyone and welcome to lesson 8.2 on properties of logarithms. To start out this video, what is this about? Kind of zooming in here and looking at this table right here, which shows the exponent rules. These are things you know or should know from the past, from Algebra 1, and from our work with exponentials so far through Algebra 2. For example, if the example, you have product rule, right? If you have two bases multiplied, then you add the exponents together. An example of that might be like x squared times x to the 7th. This would be x to the 9th, right? And this is because x squared is 2x's, x to the 7th is, let's see, 3, 4, 5, 6, 7 x's, which totals up to 9, thus the rule, the addition. Right? You don't multiply them, you add the exponents. Similarly, with division, you subtract the exponents and so on, right? You can kind of pause and maybe read through these, right? Raising a power to a power, like x squared to the 7th, that would be x to the 14th. That's in a situation where we multiply. The zero power rule, negative exponents, and rational exponents, as talked about in Unit 6. So these are all the exponential rules that, we kind of have to remember, recall, and use throughout this unit because we are talking about exponentials, but we're also talking about logarithms. The point of this video, though, is not to go over the exponent rules, just go over the logarithmic rules. So these log rules actually can be derived from the exponential rules, and they just make sense because of that. So some of them are self-evident, like log of 1, right? We say that log base b of 1 is 0. And if you think about the logarithmic conversion that we've talked about in the previous video, log base b of a equals x becomes b to the x equals a. Well, there's a rule that says any base to a power of 0 is 1. And if you convert that to logarithmic form, then that would say log base b of 1 is 0. So it's just the fact that anything to the power of 0 is 1 leads to the fact that log base b of 1 is 0. And a lot of these rules kind of come about like that, like log base b of b is 1, and so forth. I am probably going to make a separate video for the proofs of these three rules. Now, that second video will be optional. You do not need to know the proofs, but the main three rules we're going to use in this lesson are the product, quotient, and power rule for logarithms. And here's what they say. The product rule is kind of like the exponential product rule. You see, if you had x squared times x to the 7th, we said that that's x to the 9th, right? You add the exponents when you're multiplying bases. Well, if you're adding logarithms, then you can combine that into a single logarithm with the arguments of each of those logarithms multiplied. What? Right? Here's an example. If you said like log of 3x, you could separate this into log of 3 plus log of x. Because 3x is connected through multiplication, thus they're separated like this, yeah? Another example is if you had log of 2 plus log of 5, then you could combine these logs to make log of 2 times 5, which would be log of 10. Also, we know log of 10 because log base 10 of 10 is 1, right? So this is kind of an example of the product rule. The quotient rule is the exact same thing, but subtraction. If you're minusing the logs, you can use division of the arguments. And then this last one that we're going to be using and looking at is what's called the power rule. This one's my favorite, and it's really interesting. There's not a lot of functions, none of the functions we've studied do this. And what it allows you to do is if you have an exponential inside the logarithm, you can actually take the exponent and whoop, put it out to the side as a coefficient on the log. You say, what? Really? You're allowed to do that? I said, look, here's an example of this. Let's say we had log base 2 of 8, right? Well, first of all, we know log base 2 of 8 because if you convert that to exponential form, if you say this equals something, Then as an exponential, this would say 2 to what power is 8? The question mark, the thing we don't know, would be 3, because 2 cubed is 8, right? So we know log base 2 of 8 is 3, just because it kind of answers this basic exponential question. But let me show you something. Log base 2 of 8 could be rewritten. Observe. Log base 2 of 8 is the same as log base 2 of 2 cubed. And via this power rule, what the power rule says is you can take that 3, the cube, and put it as a coefficient on the logarithm, like so. And say 3 log base 2 of 2. Thing is, we know log base 2 of 2 because that's 1. And so 3 times 1 is 3. That's the same answer, yeah? This is not a proof. This is just kind of a verification of the property, showing that it does indeed work for, for an example like this. Again, I'm going to make a video where I kind of prove those. It's not going to be a long video, but just if you're interested to see why are these really true? Why, is it just because Mr. Spake says so? No. They come from the exponential rules, and you can prove them. There's a few more rules here. I'm not going to explain them too much. You might see them pop up, but they're not a heavy emphasis in this unit. This property says if you have a base and you raise it to a log of the same base, they essentially cancel out, right? So like if you said 3 to the log base 3 of 2, the 3 and the log base 3, because the log base 3 is in the exponent, would sort of cancel, and you just get 2. And if you're asking why is this true, well, it could kind of be quickly proven or shown, demonstrated. If you say 3 to the log base 3 of 2 is x, because we don't know what it is, right? Then if you do a logarithmic conversion where b to the x equals a becomes log base b of a equals x, then the b is 3, so it's log base 3. The argument a is this a, which is this x, so this would be x here. And then the exponent x is actually this exponent, which is log base 3 of 2. And then you say, oh, well, look, log base 3 of x equals log base 3 of 2. The conclusion must be that x is 2, right? Thus, it's 2. So that's why that rule kind of works, is it's just inverses. They inverse each other. The equality rule is actually that thing we just said. If log base 3 of x equals log base 3 of 2, then x is 2. X equals 2. That's what that says. And then this last one, I really like this. I kind of wish we had more time in the unit. If this unit was a little bit longer, like 1 day longer, we might do change of base rule, but we don't really have time, and that's okay, because it's a little bit outdated. What this says is if you have a logarithm in a particular base, you can re-express it as a logarithm in a different base. So let's say you had like log base 3 of 4, right? The base is 3. Flashback to early education, prior to calculators, digital calculators, we couldn't calculate, or we didn't have log base 3 calculations on hand. We had calculations for log base 10 and calculations for natural log. So what you could do is you could change this to base 10 and say, okay, you could say log base 10. You don't have to write the 10. You can say log base 10 of 4 over log base 10 of 3. And you don't really need the 10, so you could just change this to log of 4 over log of 3. And the decimal value of this is actually going to equal the same decimal value of that. Again, this can be proven, not going to prove it, but to sort of show you that it's true, if I come over here, we were doing matrices, I guess. Let's see here, math, I'm just sort of demonstrating this to you. Log base 3 of 4, you get this decimal, right? But then I said you could do common log of 4 over common log of 3, and you get the exact same decimal. You see the 1.26. It's calculated right there. So it does work. It is true. And it's a way of converting logarithms into different bases. Because, look, if I had like an expression with multiple base logs, like log base 2 of 3 plus log of 3. Well, they're not in the same base, so you can't actually add those, but you could rewrite log base 2 of 3 into common log and then do math with it that way. So it's just, it's just a neat thing that you're able to do. Anyway, the three main ones you need to know from all that are the product, quotient, and power rule. And I'm going to work a few examples demonstrating that, and that's going to wrap up this video here, okay? Because it's quite a short lesson. Even though I did a lot of talking right there, it's a pretty short thing to do. So we have a few examples here. We're going to go through all of them. So the first goal, fully expand the logarithm, right? So the quotient rule says if two things are multiplied, you can separate them into addition like so, right? And that's the product rule, product multiply. The quotient rule is if they are divided, then you can subtract them, right? That is what both rules say right there. Now, if I jump to this logarithm and I look at the argument x times y divided by 3. Well, the way this is going to separate is log base 3 of x plus log base 3 of y, because those added is log base 3 of xy, okay? Then minus log base 3 of 3, because it's divided by 3. If we said log of x over 3, that would be log x minus log 3. Yeah? So if it's on the denominator, if it's subtraction, right, it goes in the denominator. That's pretty much it. And if it's addition, it's going to go in the numerator. It's going to be multiplied. Also, looking at this expression, we actually know log base 3 of 3, that thing at the end there. Log base 3 of 3, 3 to what power is 3? 1. And so, we kind of simplify the expression a little bit through that expansion. And this is really just we have two goals that we're going to really be doing is just expanding and condensing. Yeah, expanding and condensing. This is what is meant by logarithmic expansion, is you take this single logarithmic and then you sort of expand it, blow it up into simpler, separate logarithms. Okay? Let's see one more example of this expansion. This one is just to see, we talked about e, we talked about natural log. This is an example of that in action. So if you look at the argument, it's 2 times e cubed. So this is separated through addition. So it's going to be separated as natural log 2 plus natural log of e cubed. Now remember, natural log is in base e, right? ln is, I'm going to say log base e. So log base e of e cubed. See, this is asking, what power do you put on e to get e cubed? You put 3, yeah? Just the number 3. So natural log of e cubed is going to come out to 3, like so. And that's it. That's our log expansion. Those are those two things added. Okay. The next examples are just condensing. So doing the exact opposite. That's taking these logarithmics and condensing them into a single expression. Remember, we're also going to use what's called the power rule, which if you have x to the n inside a logarithm, you can take the exponent out to the side as a coefficient. And on the same side of that coin, if you have a coefficient on a logarithm, you can choose to put it in the exponent of the argument. And that's actually what we're going to do when we do condension. Which I don't know if that's a word. But when we condense logarithms, we're going to take that coefficient, put it inside. So for log x, this is going to become log x to the 4th because of the power rule. Same situation with 3 log of 2y. This is going to be log of 2y cubed. So the cube is actually going on both 2 and y multiplied. And then log z is just log z, so we're not going to do anything with that. Do note here that the 2y cubed, that cube applies to both. So real quick, I can say that 2 cubed is 8, and then there's the y cubed, okay? We are allowed to distribute that exponent such. It's one of our exponential rules from that table. And then what I notice here is, you have a positive log here, a negative log, and then another positive. Well, the positive ones are multiplying in the numerator, and the negative goes in the denominator. Because this component right there, right, those two logs are logarithmic division using the quotient rule. X to the 4th over 8y cubed. Oops. That's what this says. This would become that, yeah? But then it's plus log z, and that just means this fraction times z. And the thing about these fractions is if you're multiplying a fraction times a constant, the constant just goes in the numerator. So you can kind of clean this up, put z in the numerator with x, and thus we are done. And so that's kind of the goal with condensing a log is you really don't want a coefficient here. You just want to put you want just a single logarithm of some complicated expression. Yeah, expansion is the reverse. It's basically making the thing inside as simple as possible and separated. Okay, here's example B. This is just kind of the same situation. We're going to condense this. Notice there's a subtraction. So what you could do is you could say, oh, okay, well, this is log of root 5 over, right, it's just subtraction, so it's quotient rule, so you divide root 5 over the fraction root 5 over 5. Okay? And then you could just do keep, change, flip, yeah? You just say, hey, it's root 5 times 5 over root 5. This is how you can deal with division by fractions, keep, change, flip. The root 5s will cancel, and you'll just get 5, leaving us with log of 5. Ta-da! And that's it. That one's a little simple there. Little simple one right there. So, yeah, not a big deal. Oh, I didn't want to erase that. Let's just keep that there. Okay, and that's kind of it. That's all this lesson is just expanding and condensing. Though we have a couple more things to show. This example shows how you can use these properties to simplify a logarithm completely. And so we're just going to use laws of exponentials and in logarithms to condense this and, if possible, simplify. So the first thing here is I'm going to use the power rule because in general, when you're simplifying, you might want to, I don't know, combine them, though sometimes you might want to expand them. So the word simplifying doesn't really, you could be expanding or you could be doing whatever. So this gets us log base 8 of 2 to the 7th and log base 8 of 4 to the 4 squared just by power rule. Now, one way to do this is to just crunch the numbers and go. So I'll kind of show that method real quick. This would be log base 8, 2 to the 7, right? 2, 4, 8, 16, 32, 64. Let's see, 1, 2, 3, 4, 5, 6. Okay, we only need one more, 128. So that's the 7th power. So this would be log base 8 of 128 minus log base 8 of 16. Okay? Log base 8 of 16. And then you would just have to do 128 divided by 16. Problem here is that's, I don't know, kind of not fun, 16 times 10 is 160. 16 less than that is what is that? 34? No. 44? Yeah, 144. And then 16 less than that is 128. So this would end up being 8, meaning this is log base 8 of 8. And hey, log base 8 of 8 is 1. Thus, our answer. Okay? Now, the thing is, I don't actually like that. I don't like 128 divided by 16 because, I don't know, if I don't have a calculator, and you wouldn't get a calculator for this because the thing is if you had a calculator, you could just type this in anyway, right? So like, why would you use a calculator for division if calculators are built with logarithms in it anyway? So you would want to do this by hand. So one way, crunch the numbers, do that. Another way, which I actually like more, is to play. You say, what? Play? Play with what? Say, play with the exponents. So watch, I'm going to redo this one again. 2 to the 7th is just 2 to the 7th. But 4 squared, being 16, is also equivalent to 2 to the power of 4. So what I'm actually going to do here is rewrite 4 squared as 2 to the 4th. And the reason I'm going to choose to do that is because if you do, if you put those in the same base there, then it's subtraction of logs. Quotient rule means you do 2 to the 7th divided by 2 to the 4th. Oh, but wait. Since they're the same base and you're dividing them, that's exponential subtraction in the exponents. That's 2 to the 7 minus 4, right? Which is log base 8 of 2 cubed, which I'm gonna write right here. 2 cubed is 8, which comes out to 1. Now, was it more writing? Yes, but it's actually kind of like less work in a way. It looks like more work, but if you recognize that 4 squared is 16, which is 2 to the 4th, then you can sort of use exponential rules to quickly get the answer that way, as opposed to like thinking about division of 128 divided by 16 and crunching it out. Both ways are valid. I don't care what you do, but this is a more creative approach, and I kind of like this method. Maybe you do too. I don't know. Maybe you like the crunch method. I don't know. Maybe you like to just brute force it. Okay, one more example. So reminder, so what's unique about this one is the 1/2. So power rule would suggest that I can put that half as the exponent on 9, like so. Well, here's the thing. We've learned that a fraction, power, means a rational expression. And in fact, a power of a half means square root of 9. Yeah? And we know the square root of 9 is 3, thus simplifying that logarithm individually a little bit. Okay? So, yeah, you see how I'm writing out the rest here, but really, the log base 6 of 12, he's just chilling. He's not doing anything. The half came on the power of 9, which is a square root, which becomes 3. And now, since you're doing logarithmic addition, you could say, oh, this is the product rule. This is log base 6 of 3 times 12. Of course, 3 times 12 is 36. And if you ask, hey, what's log base 6 of 36? That's asking the question, what power goes on 6 to make 36? Oh, 2, right? 36 is 6 squared. Thus, I have the answer 2. Okay, so that's how that is done. All right, one more example, and this is rewriting expressions as a single logarithm. So this rarely comes up, but it's a good algebra technique to be aware of. A lot of times, you might be working with logarithmic functions, and maybe you want a single logarithmic thing. You don't want like a bunch of plus, minus, separate terms. Maybe you just want something all together in one. This is a way to kind of force things that aren't logarithmic already to become logarithmic. If you don't know what I mean, watch. So look. So here's log base 10 minus log base 5 of 10 minus 2. The goal is to rewrite this value as log base 5 of a number. Yeah? So the minus 2 is not part of this logarithm, right? Think of it as a bar right here. It's log base 5 of 10 minus 2. Normal 2, not logarithmic 2 or anything like that. And if you think it's as easy as log base 5 of 8, well, that's wrong, because you don't combine logarithms that way. And if you think if it's log base 5 of 10 over 2, well, that's also wrong, because the quotient rule is through division from logarithms. So the goal here is to actually change 2 to be in log base 5. That way you can combine them. So log base 5 of 10, that's just log base 5 of 10. But what we might do here is we say minus, and you say, I need a logarithm. I need to change 2 to be in log base 5. Yeah? So if this number's 2, then log base 5 of what is 2? Thus, you're saying, oh, log base 5 of, let's call it x, is 2. Then if you want to know x, turn it to an exponential. The base is 5, the power is 2, so that's x, and 5 squared is 25. So that's to say, oh, log base 5 of 25 is 2. And now, this 2 is in terms of log base 5, which means you can combine these logarithms. So quotient rule would say that, oh, this is log base 5 of 10 over 25. And of course, 10 over 25, that's a nice fraction that's going to simplify as 2/5. And thus, we achieve our result. We achieve our answer. That which we wanted. And to show you that this is the same, right? Log base 5 of 2/5 is the same as log base 5 of 10. Minus 2. I'm going to do log base 5 of 10 minus 2. Okay, it's this negative 0.569 business, right? And then, to show you, I'm going to do log base 5 of, what did we say, 2/5? 2 over 5? Same decimal value. Ain't that nice? Look at that. And so it's just a way of kind of putting those two things together, kind of doing that. Okay. Rarely is it needed, but it is something to look out for in this unit, because you're learning about logarithms and you're learning about their properties, and the class is algebra, and it's just about algebra techniques. Now, it's not only about algebra techniques, but that is a lot of what we talk about. Okay, one more, and then we're done with the video. Same thing, but this is a function now, which is probably more so when you would use this to change functions to play nicer with one another. Okay, so you got 3 log base 2 of x. Via the power rule, we can put that 3 on the exponent on x right there. Okay, so that's just log base 2 of x cubed. Now, same situation. The number, the constant, 1, needs to be put in log base 2. So you would say, oh, log base 2 of what, right here, log base 2 of what number is equivalent to 1, right? Again, this is just asking 2 to the first power would be 2. So if we didn't know, right, log base 2 of x is 1. As an exponential, the base is 2, the exponent's 1, this is x. Thus, x is 2. X is 2 to the 1, which is 2. And now that they're added like this, right, the addition of logs can be combined via the product rule, thus multiplying our logarithms as 2x cubed. Ta-da! And so we have it. Yay! Woohoo! Yippee! Right? And I have this expression. And again, in math, sometimes this expanded expression is actually going to be preferred. Other times, the condensed one might be used for something, you know. So this is just kind of the practice of going back and forth. Okay, that'll do for this video. These are the properties you really need to know. Again, it's just these three. Some of these other ones, you may see them on the homeworks. You know, you can refer to the sheet and all that good stuff. But just know, these three rules are not provided on the exam. You gotta know them. They're not that hard to remember, really, but you have to know them. And keep in mind, and I think the thing you want to watch out for the most is don't get them backwards, right? So a common student mistake would be log of x plus y is like log of x, log of y. Okay, no, not true, right? So you don't want to do that, okay? And that'll do. Part 2 of this video is just going to be me proving some of these rules. If you're interested, though, if you don't want to watch it, you don't need to watch it, all right? Okay. Thanks for watching, and I'll see you later.